Hello, everyone. Welcome to this Gatan webinar on in-situ TEM with the K3IS. My name is Ben Miller, and I'm an in-situ application scientist at Gatan. This morning, I have the privilege to introduce Dr. Katie Young-Johan and Dr. John Watt, who will be presenting together today. Katie Young-Johan is a staff scientist at the Center for Integrated Nanotechnologies, or CINT, working on developing new capabilities for in-situ TEM imaging of environmentally relevant materials processes, with a current focus on energy storage interfaces and corrosion mechanisms. And she's the thrust leader for the in-situ characterization and nanomechanics thrust at CINT, and the co-leader of the Microscopy Society of America's focused interest group on electron microscopy in liquids and gases. John Watt is a scientist at the Center for Integrated Nanotechnologies as well at Los Alamos National Laboratory. His research interests include the synthesis and in-situ TEM characterization of inorganic nanomaterials and their unique interfaces. He also runs CINT's cryogenic electron microscopy suite that was recently established to provide advanced characterization to the soft matter and nanomaterials community. So now without one more thing. As we're going through the webinar, if you have questions, you can type these into the questions pane as you see here on the screen. And you can type those in, and at the end, hopefully we'll have some time to ask questions to the speakers live. And if we don't get to those questions at the end, we will try to address them one by one and send you an answer. So feel free to ask questions through the questions pane as we go. And with that, I'll hand it over to Katie.
Great, thank you, Ben. So as you said, we are at CINT, and this is showing the microscope that we were using for these experiments. So it is a Titan environmental TEM. It's image corrected, monochromated, and we had the K2IS camera on there, and then we swapped it to beta test this K3IS camera. So we were experienced with these types of cameras before, and we are an institution that offers free access to these tools with the acceptance of a 2-page user proposal. So we're actually one of the 5 NSRCs in America that offer these types of capabilities. So we had many holders for in-situ analysis that are compatible with the microscope for high temperature heating, straining, vacuum transfer, electrical biasing, as well as cryogenic temperatures. And then of course, being an ETEM, we have a gas cart for delivering gases into the pole piece of the microscope. And so let's go next slide. I'm going to start talking about experiments looking at lithiation dynamics. So as Ben said, I do a lot of energy storage, and we have a lot of user proposals that look at energy storage. So on each of these slides, we're going to try to acknowledge our partners in our user community that are working with us on these experiments. So let's go to the next slide. The first thing I want to bring up is that when you're looking at lithium materials, lithium is very beam sensitive to the electron beam. And so this is showing not on the K3IS camera, this is just on our standard 4K CCD camera, that after 7 minutes of imaging at a fairly low beam current, this was reducing the beam current using the monochromator, you can see that the lithium metal is just disintegrating under the beam, and which of course would make it very hard to image reactions or to do high resolution imaging of the lithium metal under these conditions. And so if we go to the next slide, what you can see here is There's very low contrast in these images, and I tried to add some lines in here, but this is imaging the same lithium metal at a much higher magnification. You're seeing here that there's lattice in these images. So the one thing I'll say about the K3 camera is, you know, you're collecting over 4K by 4K pixels in the images, and so you need a really high resolution monitor to see some of the details in these images. And so that's why I added some lines here. But this is just showing that I was acquiring a movie for about the same time as what you saw in the last slide, and we're still able to retain that lattice information during the movie. And so this is just showing that, you know, with this very sensitive camera to very low dose imaging, we can still obtain high resolution information without damaging the structure too much. And that's very important for these lithiation experiments, because if you're trying to do an in situ movie, then, you know, we're collecting a lot of frames over a certain duration of time, and we don't want to be destroying the material while we're imaging it. So we can go to the next slide. Another example of beam sensitive materials are solid state electrolytes. And so on the left side, you're seeing kind of the structure, which is a silicon support, and then silicon carbide as an electrode, and then this electrolyte, which is a polyvinyl alcohol based electrolyte. And so these are sensitive under the electron beam. We've seen previously that when you're imaging these for prolonged times, that the electrolyte will start to bubble and form voids within that structure. The video that's being played on the top left is showing that interface between the silicon carbide and the electrolyte, and that we're not seeing damage. And this was actually under 2 volts bias between 2 electrodes in the electrolyte. And so what you're seeing is nothing really happens, and that is a good thing for this experiment, because we didn't want to be damaging the electrolyte with the electron beam. So let's go to the next slide. The next series of experiments I'm going to show are based on these open cell lithiation studies. And so on the top left, you have an image of the Nanofactory STM TEM holder. And so this is the setup where you have on one side a probe with generally you get some lithium metal. For all these experiments I'm going to talk about, we got some lithium metal on the end of that probe. The opposite side, where you're seeing a TEM half grid, is where you mount your sample onto a metal wire. And then you can apply a bias between these 2 electrodes. And then you can also use the probe to move and position contact with the part of your sample that you're interested in. So this has been done for over a decade now at CINT. And on the right are some beautiful results that were previously obtained, showing that you can obtain atomic resolution information. But you can see here that this is a very small field of view that you're acquiring for these types of experiments. And so what you can pay attention to in the next slides is how much we're able to collect by using this camera in combination with this in situ holder. So let's go to the next slide. So what we're trying to do is to track the structural changes that's occurring inside of these materials as they're being lithiated. And so this is a user at Florida International University, Dr. Wenzi Lee, who synthesizes these nickel sulfide filled carbon nanotubes, and different filling inside the carbon nanotubes. Previously, you've observed that as those structures lithiate, that the filling kind of moves through the carbon nanotube as there's volume expansion, because you can imagine, you know, moving lithium into a lattice, you have this volume expansion, which is very well known to cause degradation mechanisms, to fracture or damage the material, where then you're not able to keep recycling that structure. And so watching this in the TEM, here on the bottom left, we have the lithium metal. Then there's an open area of unfilled carbon nanotube, followed by the nickel sulfide filling. So if we go to the next slide, what you're going to see is a video of this reaction of lithium interaction, lithiating the carbon nanotube filled nickel sulfide structure. And so initially there's some volume expansion, and you can see that the carbon nanotube is being pressed out, and on the bottom left of the movie, it's moving as a front, and then it gets, and so that front is progressing as the lithiation front is moving along. In the right image, you can actually see there's a difference between structures that were lithiated and unlithiated areas, and that a lot of the reaction was moving down that inner wall of the carbon nanotube. And so this is just showing the high rate capabilities of this camera, and also a very large field of view, so that we don't have to, physically move the sample holder while we're trying to collect the data, but that we can just set it up and let the camera collect as this process is occurring, even though the wire is moving a pretty large amount over the time. Okay, so if we go to the next slide. Okay, here is just showing, images of the degradation of the wire. And so again, with the camera, we're able to do really low dose imaging with, and we can do the high speed imaging seamlessly. And so we don't need to switch between different modes as you did when you had the K2IS camera. And so this is very advantageous, because then you're still able to take very high resolution images of the structure before and after the in situ process, without delays in calibrating the camera. And so this is just showing that, these images were collected right after the movie, and then we can also look at the movie right after we've captured it to assess the quality of the data. And so here we're just observing that in different parts of the carbon nanotube that there was actually fracture that occurred due to that volume expansion of the nickel sulfide under very high lithiation rates. Okay, so next slide is just, this is just highlighting again that we can get information about how the structure lithiated by observing what areas are lithiated and which areas are not. And so watching that the lithiation front did move down that inner wall of the carbon nanotube is fairly obvious in these images. So next slide. Okay, here we have a different kind of structure. So these are very small tin oxide aggregates of nanoparticles that are decorated on top of a carbon nanotube. And so it's known that tin dioxide has a very high storage capacity, but there's also a large volume expansion. And so by nanostructuring these crystals, the idea is to prevent that pulverization, the breakdown of the nanocrystals while you're cycling. And so these are very hard to observe in the TEM because they're such small nanoparticles and small aggregates. And so we have to be at very high resolution to observe what's happening in the individual nanostructures. So if you go to the next slide. Here's the setup. So on the left again is a tungsten probe with lithium metal on top, and then going to contact one of these tin dioxide coated carbon nanotubes. And so on the right you're seeing a line in yellow of where the end of the carbon nanotube is, and then that aggregate on top. And then in the next slide I'll show you the video of this process. And hopefully your monitor will see that there is a lot of lattice information, especially in the carbon nanotube. That played really fast. But on the left in the image, you can see that on the top, you're seeing that the lattice of the tin dioxide nanoparticles goes away. And so as they're lithiated, they become amorphous. But we retain the lattice information in the carbon nanotube because that is untouched during this process. And so with a higher frame rate, we can go through image by image and observe how the lithiation is taking place, if it's happening particle by particle, if it's happening from the internal of the particle or external to the center, and then how quickly it moves through the different particles in that aggregate. So the next slide. So this next is a different example. This is a tellurium nanowire, which is a single crystal. On the left, hopefully you can see it's a nice lattice on the edge of the structure, and the FFT is showing that. Then on the right is a video, and intentionally you can't really see what's going on. It looks pretty blurry. There's not a lot of detail in these images, and you might observe that there is some lattice in kind of the center, in the bottom half of the image. There's some lattice that retains during the duration of the video. But we can go to the next slide. But we know that, you know, it did change from a single crystal into a different crystalline structure. So next slide. Yeah, and then that's also shown in a large morphology change of the nanowire, where before it looked like a nice single crystalline structure, and then here it's all bent and it looks like many particles within that structure. And so next slide. What the K3IS can actually do is you can use Python scripting to look at what's happening in these videos. And so what has been done here by a postdoc at Sandia is to perform sectioning of the video. Oh, I got a feedback. And so the video is cut down into a matrix, and then each of the different segments of the video was observed, where we performed an FFT to look at a periodic structure, and then to identify, as the video plays, where those periodic structures show up. And so on the left is a 20 by 20 matrix, and then on the right is a 40 by 40. And so here you're seeing that throughout this video, there actually is a lot of lattice information that's coming in and out of the different frames. And so this can help you kind of identify which frames are of interest. And I think the number counting is in microseconds of the image being played. So I'm just showing that, you know, there are strategies that we can use and integrate with the K3IS so that we can do real-time analysis of the data right after we captured it, so we know whether or not we need to go and probe a different structure, or if we've obtained the information that we need. So next slide.
Okay.
And then I'll hand it to John.
Yeah, thanks, Katie. Thanks, Ben and Gatan. So we're going to shift gears a little bit here and talk about magnetic nanoparticles and how we've been using the in-situ TEM, the ETEM, and the K3 to kind of understand some of this behavior and really get a complete picture about, you know, the synthesis and optimization of these magnetic nanoparticles. So here we're going to use quite a few of the different techniques that the K3 has in its toolbox, and just kind of show how we can get little different bits of information to kind of complete this picture. So specifically, we're talking about magnetite, Fe3O4 nanoparticles, so iron oxide. So these are used quite a lot for, you know, biomedical applications such as hypothermia, MRI contrast agents, and magnetic nanoparticle imaging, MPI, but also in industrial applications. So as a soft magnetic component, for example, in inductors and transformers. But one of the, you know, the kind of key takeaways for all these applications is that in synthesis, they basically require the same kinds of things. So you want good size and shape control in the particles. You want a tight size distribution. Any type of polydispersity in the sample means that it will behave non-uniformly in any type of applied field. So we want that whole particle ensemble to be behaving uniformly. We want nice, good crystallinity, and we also want to understand interparticle interactions, because the way that particles interact in solution or in your application can change how you believe that they behave in the presence or absence of a field, or, for example, a switching field in the case of inductors and transformers. So in terms of size and shape control, we can get very good size and shape control down to a very low coefficient of variation. We can control the size and shape predictably and reproducibly, as shown on the right here. But there has been some evidence in the literature of defects in magnetite leading to a reduction in MSAT. So this was done from Sarah Majetic and collaborators. This was done at the University of York on their ultrastem. So they showed that from some literature syntheses from different groups that the reduction in magnetic saturation is due to kind of internal defects, things like antiphase boundaries. So controlling and understanding the inclusion of these defects is really important in having a high-performing material. And in the synthesis of magnetite, there's often this wustite to magnetite oxidation step, and it's this step here where we can see the inclusion of these defects. So this is done on a CEDA camera, but this is just kind of showing some of the preliminary work. So this is an ex-situ oxidation in air at high temperature, and we can see that we get the inclusion of defects when we have such rapid oxidation. So this is in collaboration with Dale Huber from Sandia National Labs, and we have a fairly good but relatively low MSAT of 69 amp per meter squared per kilogram. Bulk is around 90. When we do a slow controlled oxidation, this is at a much lower temperature, we get a nice single crystal, and we start to reach kind of closer to those bulk values. So we really want to understand, what's going on here in terms of the oxidation step. Can we observe it in situ in the ETEM and understand the kinetics and dynamics of what's going on there? So having the K3 was really fantastic in terms of answering some of these questions. And I'll kind of go through, the distinct capability of the K3 and why it was such a help. And the main one really for nanoparticles is this wide field of view. So typically when you're doing these types of nanoparticle characterization, so this is, this scale bar is about 10 nanometers, and so we're probably at maybe up around 250 to 300,000 times magnification to get that atomic resolution. With the K3, now we're back at about 34,000, so we're magged back quite a lot, and our field of view is much larger. So instead of looking at 1 or 2 nanoparticles, now we're looking at tens of particles. And these select regions of interest and the associated FFTs, you can see that you're still getting this atomic information from this wide field of view. So now instead of just kind of zeroing in on a single particle or 1 or 2 particles and hoping that you capture the event, now we can capture a very wide field of view, which gives us 2 things. If we're looking for a particle on a certain orientation, we can just take this picture and then we can go back in later and say, okay, well, it was this one here that was oriented the way that we want to see the transformation, so let's focus on that region. The other thing unique to other cameras is now that we can start to get statistically significant information on things like nanoparticle crystallinity and transformation. So this is another Python script that Ben from Gatan actually wrote up, and so here he's implemented this color wheel, which if you look in the FFT and you look for your presence of a spot, so if you have, say, the 100 spots or something over here, then these are going to be shown as blue, and likewise green and red and yellow around this color wheel. So now we can start to see the way that these particles are oriented in relation to each other, which for magnetic nanoparticles is really important, because as they dry, you can have things like induced dipoles, which induce some kind of correlation in their orientation. These are super paramagnetic at room temperature, so we would expect them to kind of be oriented randomly, but these induced dipoles can introduce some kind of unexpected behavior, which is really important for us in terms of understanding their behavior in a switching field. So we can apply this to a number of different experiments. So these were oxidized ex situ, and we're still trying to understand this data, but you can see that You know, these are fairly low dose images, but you're still able to extract this information from each individual nanoparticle, and we can start to see some differences between the low oxidation and the high oxidation. So we're super excited to delve deeper into this data. Another one of the techniques that was really exciting about the K3 is 4D STEM. So here at each point in the STEM raster, you get a diffraction pattern. So with the K3, you can get a very high pixel resolution of the diffraction. So here we're taking this region of interest, and it's giving out this diffraction pattern, which is probably pretty hard to see. But then what we can do is circle this very faint reflection here. And then when we move to the next image, we can start to see which particles around the central particle have that same orientation. And not only what particles, but what part of the particle. So you can see here that, you know, in terms of this crystallographic orientation of the core of this particle, we're seeing some out here on the shell. So again, we really still need to understand what's going on here. But it's quite powerful being able to switch between these two modes on the same camera and start to get kind of complementary information that we can then start to build the story. So now we're moving to in-situ. So, you know, with the high speed and low dose, we're excited about the K3 because, you know, this is in the TEM, and so we are at temperature and we are flowing oxygen gas. So there is already a number of variables in the system. So introducing, you know, a high energy electron beam can obviously kick off some transformation, perhaps earlier or later, or when, you know, you want to be able to mitigate the influence of the beam. And so, you know, being able to image at low dose, but also being able to image at low magnification is really unique in terms of being able to capture the transformation without that second external influence of the beam. So we're at 56,000 kx here. It's 10 electrons per pixel per second, and we're operating at 25 frames per second. So looking at this image, it's not very bright because this is a single snapshot of that video. So there's a few things in the K3 which are really useful, especially when you're coming from a CETA camera where you're used to looking at quite a bright, high contrast image. So built into the K3 user interface was a thing called live frame averaging. So essentially it would be summing frames to give you a brighter image as you're looking at the image. But in the back end, it's still kind of, you know, taking all of that data. So you can go back and you can pull out these images like this. The other thing that was really useful is this look back feature, which you can set up to 5 seconds, if I'm remembering correctly, where you can basically be taking video the whole time while you're looking at the live frame averaging. And then if you see something that you want to capture and you don't quite hit the play button in time, it'll go back and record the video from 5 seconds prior. So that means that you're always going to be able to capture your event of interest. Again, looking at this and thinking about these movies that I'll play in the next couple of slides, is that we are taking this wide field of view image, so you know, the full field of view of the camera, but then when we go to process these images, we can look down onto this select region of interest. So here we're watching the in-situ transformation of wussite under an oxidative environment in the TEM at temperature. So again, just to reiterate, this whole field of view, all this data is sitting there and has been captured, so tens of particles, but we're just zeroing in on this region of interest here. So if we play the video, you can see hopefully that you've got nice atomic resolution. So these are framed, so 10 frames are summed and presented at 20 frames per second. And you're seeing that you have nice atomic resolution. We'll see this contrast here if you look at these 3 particles in the top left there. You'll see that contrast starts to disappear. So we have some transformations happening there. Again, we need to understand this better. But I think the key takeaway from this is that you are getting this information from all of these particles. So even if you come down into this region and you look at your particles and what's happening, and you don't quite capture a particle on the orientation that you need to really see the transformation, then you still have all of these particles available to go and analyze. This is high speed of the camera at low dose, and this is at very high temperature. So this is a little more grainy because it's high temperature and there's much more gas. This is pushing the limits of the pressure allowed in the octagon. And here we see that these particles come together and they facet on the side here before they coalesce. So you can see some strong faceting happening here before these things coalesce. And I think that's it for magnetite. Katie, if I hand back to you.
Yeah, so as we are a user facility, there was other projects that came to our door, and so we were just going to show some other examples of using the K3IS camera for these different projects. So next slide. The next two examples are 4D STEM maps, and so this was of a tellurium nanowire, and so this is looking at using 4D STEM to map strain within an individual nanowire. And you can see on the left side of the image that this nanowire is very small. So it's less than 10 nanometers in diameter, but still they are able to very accurately measure the strain throughout that nanowire, which you can see on the right side there, looking at different sections that were subjected to different amounts of strain as it was. And then the next steps of this type of work is then to apply your own strain or to apply a different environmental condition and see how that changes the inherent strain in the nanowire. So next slide. So then this is an example of looking at stainless steel and using the TEM to understand the impact of hydrogen on the structure. And so Julian was interested in looking at, again, the strain around some dislocation pileups in the material. And so using 4D STEM, he was able to take a before and after strain map of this region. And so what's being shown here is just the before image, but you're seeing that there's a lot of strain around that dislocation pileup, and then the strain is reduced in some areas on either side of it. And so, by using the TEM and using this camera, you have a lot of versatility in these types of experiments for getting a better understanding of relationships between structure properties and environmental impact. So we can go to the next slide.
Okay, thanks. So yeah, this is looking at some examples of transformations of inorganic catalysts. So that's one of the main interests in the TEM is putting these inorganic substrates in and looking at their behavior under kind of industrially relevant conditions. So within the TEM, we can go up to about 10 millibar of reactive gases, and then we have the heating holders that can go up to 1200 degrees Celsius. So we can really submit some of these to pretty rough conditions. So this is a ruthenium branched catalyst from Professor Richard Tilley at the University of New South Wales in Sydney, Australia, with some platinum nodes, I guess, on the surface. And so here we're looking at the transformation under relevant conditions, and this is to contribute to the understanding and the further development of highly active and highly stable catalysts. So again, this was taken at high speed using the K3, and then the dose is fairly low. So each frame was about 10 electrons per pixel per second. and then when it's framed, that goes up to about 100. So what you'll see here is at a certain temperature, these platinum nodes are annealed into the branch. You can see that you have some defects at the surface. You get the emergence of these moire fringes as the sample turns and that node gets incorporated, and then eventually we end up with this single crystal. So again, the wide field of view from the K3 really is fantastic for understanding these things, and now we can start to get statistically significant information. So on this next image, the ROI is even smaller, and I'll go back and forth a little bit between these two as well. So even within this small ROI here, we have a number of these nodes that we can observe. So we have the live FFT here as well on the left-hand side. So even within this small ROI, you're seeing a number of these events, and you're getting atomic resolution, well, lattice plane resolution in this image at least of these nodes annealing. So even within this, you have a number of events that you can choose. And then if you look at this image here, you have all of this information here still to be processed. So we really are now looking at, statistically significant amounts of atomic resolution transformations within the ETEM, which is just fantastic. So the other thing that I will note here on this video, this is all done within GMS. So this is all done with the tools available to the user in the easily usable user interface. So this can all be done kind of at the workstation or at your laptop. This is a manganese tin nanoparticle, which when subjected to oxidation leads to some segregation. This is with Sergei Ivanov at Los Alamos National Lab. Again, we're low dose, high speed, and elucidating the mechanism and the kinetics of this kind of oxidation in real time. So the key takeaways from this slide is, again, it's high speed. What you're going to see is you're going to see this region of high contrast in the middle of the particle segregate out to the sides to this kind of core shell interface. I'll just kind of push it forward a little bit more. You should see here that high contrast segregate out to the sides. So I guess this is another powerful thing from GMS. So compared to the other ones where we were looking at a high field of view and a number of events, this is single particle tracking and alignment done within GMS. So it's quite powerful in that sense as well.
All right, next we have work from Barry Carter's postdocs who were looking at phase change memory materials. And so this is trying to understand the transition between crystalline and amorphous of these structures with heat. And so this was using the protochip's Aduro heating holder. And this was heating it up to 500 degrees C. So here you're seeing the structure changes throughout the video from amorphous to crystalline, and so they can observe how that occurs, what the particle sizes are, and how the material kind of segregates during that process. So next video. This is some users from University of New Mexico who have made these structures that are very hard to characterize in the TEM because they are metal organic frameworks, and so they're extremely beam sensitive. I was imaging these with a cryo holder, the Gatan double tilt cryo holder, and since they are nanoscale structures, you can't just align on one area and then move nearby, because usually, where you've done your focusing, you then have to damage that area and then move to a new area. And so luckily with a large field of view, you can, with the K3IS camera, I was able to align close by on a structure where it was either over the carbon or not of interest, and then move over to where one of these nanowires was overlaid with a vacuum on the grid, and I was able to obtain, lattice scale information from one of these structures, and so, or several of these structures. So this was a low temperature to keep the dose low, but also you can see that there's very low contrast in these images, and so I think this was another huge benefit of the K3IS camera that I don't think I would have been able to acquire otherwise. And being able to see this and check out the information while I was acquiring, I was making sure that I got the data. And for cryo, you only have so many minutes of stability, especially at very high resolution imaging. And so I think that this, using the camera, saved a lot of time in acquiring this data for the user. So next slide. We just want to finish up with making everyone aware that all these tools are available at the Center for Integrated Nanotechnology. So if you're interested, we do not have the K3IS. Unfortunately, we weren't able to keep it. We will have the K2IS, and we have a lot of variety in our in-situ holders, for heating, straining, liquid gases, cryo, and then electrical biasing, electrochemistry, and then we have some custom platforms as well. We have several microscopes, and also John's in charge of a cryo suite for cryofib, TEM lamella lift out, and then of course we can use that with cryo holders or vacuum transfer holders to image structures in the TEMs. The microscope in the center of this slide is the I-cubed TEM. That's the in-situ ion irradiation TEM. And so at Sandia, that's available as well for users to come in and look at ion beam modification or ion beam damage to structures. It's able to do precession electron diffraction. And it also has a broad variety of in-situ holders, and it can actually do triple beam ion irradiation too if you need to look at multiple environments on one specimen. I also wanted to bring up that we have a user meeting this year that will be virtual. It will be September 21st to 23rd. The registration will be free, so if anyone is interested in joining and learning more about SINT and what opportunities there are for free access to tools and collaborations, please check our website. We don't have a page up for it yet, but I heard that it will be up in the next month. So check that website down at the bottom right corner. Next slide. And we wanted to thank all of our collaborators and users that helped, provide samples and helped with the imaging or providing data for using the K3IS camera. I think that it was extremely beneficial to our users, and we are all very grateful to Gatan for allowing us the opportunity to make use of this great tool. Of course, we thank the Department of Energy for our funding and allowing us to provide access to users free of charge. Next slide. So with that, well, thank you for your attention, and I believe if you're interested in asking a question, please use the chat box, and we are available.
Yes, yeah, thank you, Katie, and thank you, John, for presenting that nice work that you were able to do over the past year with the system. Yeah, so if any of you out there have questions, enter them into the questions pane. Some of you have already asked some questions, and so we'll see how many of those we can get through here while we're live. And then if we don't have time to answer your questions now, we will try to get you an answer via email over the next week or two. So please, yeah, ask questions through the questions pane if you have any. So, like I said, we got a number of questions already, and one of the first ones that came in is about Sandia and the user facility, and they ask, is the user facility at Sandia and Seant open to researchers outside the US?
Yes, absolutely. Yep. So we do have international users that come on site. That's okay, or you know, they can also collaborate with scientists to send samples. So it's the same. Just go to cint.lanl.gov, and there's links there on how to submit a proposal. There is also contact details there for the Cint scientists if you prefer to kind of discuss the potential experiments and kind of the feasibility, and then, you know, we can always give a little bit of guidance on how to submit a successful user proposal.
Okay. Yeah, thanks. So another question that just came in, what is the standard way to measure the electron dose? How do you measure the electron dose?
So that's one of the great things with the camera, is that it's actually counting all the electrons that are coming in. So for each frame of the image, the GMS3 software actually reads out what the dose is. And so this makes it very easy to track, and also to keep, you know, if you're trying to keep the same dose between different experiments, then that's readily available to you, and you don't have to do a lot of work on your own. It's just in the software.
Oh, yeah, thanks. Um, let's see. Another question that we got in slides 31 through 32, there's some drift of the region of interest, or ROI. Is the ROI tracked automatically by the software?
So there's a few, especially in this new user interface of GMS, there's different types of tracking algorithms. Those ones were just kind of the first I tried. But I think if you look at the ruthenium one, which is the one that you did, Ben, you can see that somebody with a lot more knowledge and experience with GMS than me is able to get those regions of interest to sit firmly square in the middle of the video. So, you know, I'm still learning all the tricks on how to do it. So some of the ones I think from 31 to 33 are perhaps my first crack using the tools available. But some of the ones, particularly, I'm not sure the slide number, but the ruthenium branched one, which Ben, you did, you can see that you can get that to sit, you know, that video to sit firmly in the middle without drift.
Yeah. Yeah, and so thanks, John. I would add there that you can either drift correct the entire field of view, or you can do drift correction where you select a region of interest, and then yes, that region of interest moves around the full field of view of the camera, and the final output is a video just of that region of interest, which was automatically tracked around. So it is automated, but there's some flexibility and some tips and tricks that are required there. And I guess I should also mention, while I'm talking about that, that next month I will be presenting a webinar on how to process these sorts of in situ data sets, and drift correction will be a major part of that webinar next month. So I think that may have already been sent out, invitations to that, but if not, those will be out in the very near future. Okay. Another question that came in, were the nanobeam electron diffraction strain mapping data also captured with the K3IS? And is the dynamic range of the camera good enough for this?
I did not collect that data, so I hope I'm saying this correctly, but I believe, I mean, the strain mapping was collected with the K3IS camera, and I believe that the range was good enough. I know that it took a lot of processing for them to create these strain maps. I know that Alejandra and Julian had learn these techniques from the people at the Molecular Foundry. And so I think that, the small shifts that they're seeing in the diffraction patterns, they quantified to be good enough to measure the strain. And I think that the very large detector of the K3IS camera helped with that, because then, little pixel shifts, they are able to see much easier than if you're using a smaller camera.
Okay. Yeah, thanks. All right, let's see. So many questions. So how do you evaluate the critical electron dose before you're getting beam damage in your material? How do you determine that? The critical electron, like total electron dose, I guess, or maybe they're referring to the critical dose rate. I'm not sure.
I think,
well,
I mean, for some of the really beam sensitive materials like the lithiation, some of that we did, the experiment with and without imaging, and then look for differences in diffraction. But I mean, I've had a lot of experience with these materials and these types of experiments before, and so usually it was fairly obvious to me when I was seeing damage that I thought was beam damage. And a lot of times, you're losing structure, or you're creating voids, or you're losing lattice information. And so that's what I was trying to highlight, at least in the part of the talk that I was covering for energy storage materials.
Okay. Yeah.
I would also say that something like, the look back feature is quite useful, because you can you can start imaging your material, and then you go, okay, now that's where the damage is occurring, and now you've taken video up to that damage point, and so you can go back and kind of see, like, what was the dose that led to damage. Maybe not even the damage that you can see by your eye, but say what Katie's saying, like the loss of some lattice or something that only these types of algorithms can pick up. Having that kind of feature built in means that you can kind of nail down much closer the onset of that damage.
Okay. Go ahead, Katie.
For the MOFs, I was only able to take one image before there was damage, and that was with a cryo holder too. So those materials are just extremely beam sensitive, and yeah, it was just very obvious because you lose the lattice so quickly when it was being damaged.
Yeah. So another question we have here is how sensitive is the camera to beam damage? Like, are you going to damage the camera with the electron beam?
That was the nice thing about it, is it had the dynamic sensor protection built in. So, I mean, first off, I felt that that would kick in well before any kind of, my experience with the CETA camera, I guess, is, where I'm coming from, that would kick in and retract the camera well before I thought I had done any damage to it. then you can do gain correction and things like that and remove any type of artifacts. But I'm not sure I saw any artifacts in the sensor at all. So that was really nice. And, that's really nice for us as a user facility too, to have that kind of thing built in, because we can be a bit more confident that the camera will take care of itself, and that perhaps some more inexperienced users can't do lasting damage.
Yeah, great. And then maybe have time for just a couple more questions, and then we'll have to leave the rest of these to email individuals. So how user friendly is the camera in general?
I think that I found it very user friendly. I found that we spend a lot of time training people that come in to use the tools, and this was not a burden to train people on using the camera. I think the user interface makes it very straightforward to switch between the modes. If you want to do 40 stem or if you're doing in situ imaging, it was actually just so nice that you can do in situ and low dose imaging in the same view. And so you can just capture, a single frame, and then you can start your video. And so all of our users, picked it up very quickly and didn't have too many problems with it. So I think it's a great tool for a user facility.
Great. Yeah, I'm happy that that you guys had a good experience with it. We certainly try to try to make it as user friendly as we can. How large are the data sets that you're generating, and how do you deal with the amount of data?
Yeah, that's a really interesting one. Towards the end of the beta period, where we had the 40 terabyte hard drive, quite a bit of space left, I was not taking it easy on data collection, and now some of the data sets that I'm having to go back and look at are 300 to 400 gigabytes in size, and that's at 25 frames per second, probably 3 or 4 minute video. So you can really push it as high as you want to, really. But I would say a realistic experiment in situ TEM video around 100 gig. So having having a nice powerful laptop or a kind of dedicated server is really useful. And then it becomes more a question for the institution, really, and how do you deal with that type of data, because of the nature of our host labs. We're all hard drives, but if there's high-speed data links and things like that, then obviously that makes things a little easier.
Yes, most users that came in, we would have them bring their own external drive, and then they're able to take all the data home with them. And people that don't come on site, usually they ship a drive, and then we'll fill it up and ship it back. And we also have a processing computer here, so if they want to work on their data offline, they can do that.
Okay. Yeah. Yeah, and I would just add there that we have free tools in GMS also to process these large in situ data sets, and part of the primary purpose of those tools is to reduce down the amount of data in a smart way without losing important information. So those tools are something we provide for free. Okay, so I think we're out of time here, and certainly didn't get to all the questions that were asked. So if your question was not answered yet, we will try to get an answer to you. But thank you all for listening in and attending this webinar, and thank you especially to Katie and to John for presenting today and talking about some of their experience and their results with the camera. So thank you all.
Thank you.
Thank you, Ben.